All right, the black dot is clear, so it's done. And so, whoops. I think you have to do show.
Show.
And you also have to do matplotlib inline for a NumPy. I mean, in Jupyter. You don't need that. You don't need that in Spider, but you do in Jupyter. Okay. Try again. And let's see. All right, so here we are. Oh, show is not defined.
Yeah.
Oh, yes, okay, yes,
Yeah.
okay, yes, okay.
You need to do that for each figure or just some?
Well, the thing is that you imported plot as PLT. I typically just say from matplotlib.pyplot import star.
And I had it that way at first, but for some reason I couldn't get
Well, yeah, but
a title or something.
I don't know, but that's not that wasn't the problem.
It's frowned upon in coding, though.
Yes, I know it's frowned upon.
Because you forget where your functions are coming from.
Well, the thing is that if you're doing mathematical programming,
Right.
basically, you're always using NumPy, and if you don't, if you just import NumPy as star,
Right.
then it becomes basically like MATLAB.
Right.
So,
You can only import one package as star at a time, though, right? Or could you?
no, you can do more.
Oh.
You can, yeah, you certainly don't want to do that. You don't want to import NumPy as star and math as star.
Mhm.
That's going to cause you problems.
Really? Why?
Well, because math has a different version of some functions.
So if you import NumPy, that sort of takes care of anything you might need to do.
Usually, yes. There are very few math functions that are not in NumPy. Very few. But if you want other functions from math, I would import math with a alias. All right, so I changed my n to, maybe it didn't like 100. I'll do, let's do, I don't know, 50. Let's see if it likes that. All right, so let's see what it looks like. So you can see,
Whoa.
and I think that when Shauna K did it, this figure here kind of looks like it's getting closer and closer to something that looks kind of circular. So these points on the, or actually the fixed points are these here, where you see the clusters happening. Here, I can zoom a little bit. Okay. Hello? Yeah, everything is blowing up on me. I think Spider gave up. I think it zoomed up too much. Let's go back. Okay. So we'll try to do this. What was that? That's weird. I mean, you can see these clusters here, right? If you follow this around, it's this here. So it's a funny shape. I don't know what it is. I don't know if it's an ellipse or what it is. But these are the fixed points. These are the fixed points when you start on this circle. And in fact, if you started on another circle, you'd get the same fixed points. Because we solved for the fixed points. No, we didn't.
Which ones are you pointing to?
Well, this is where you started. These are the C's where you started. And these are the fixed points. This one is kind of where the tails are. This one. You can kind of see around. We can try to do a little bit more. If we do, maybe probably could get away with 150. I think we don't have to do quite so many iterations. 20 should be fine. Oh, that was quick. Too quick.
Something's not right there.
I think let's get rid of this.
Whatever that is.
I think it's having trouble with my maybe the spider thing is biting me. Let's try again. All right, that's better.
Maybe it's hung up. Don't do Control-Alt-Delete.
All right.
Ooh. It's
That's
like a
pretty.
big fiesta on
Yeah.
paper.
Yeah, but these are the These are the fixed points. It looks kind of like an egg.
Mm-hmm.
This circle here, you can follow this around. These are the starting points. Those
This is where we get the dark space in the figure, is these fixed points.
No. The points, all the points in the dark space will go to a fixed point.
Oh, right, okay.
But the fixed points themselves do not fill up the dark space.
Okay.
In fact, we can try that. Let's try a circle with a smaller radius. Let's try a circle of C's with this was r equals 0.25. Let's try something a lot smaller. Let's try something like 0.05. And we'll see what happens and where those fixed points are. It may look somewhat similar, but it will be a different scale. All right, so here the fixed points are so you see the scale here is just on 0.05. So the fixed points are not that far away from the starting points. Okay, so you can't see it, but these points are moving slightly. And of course, 0 is a fixed point of 0. So once you start at 0, you won't move from 0.
What was the one that what did we put in the other day that was bouncing, oscillating?
Yeah, all right. So that's what we're going to get to next. All right. So, and then these are, well, this is interesting. These are the evens.
Mm-hmm. Which don't look that different.
Yeah. And these are the odds.
And they do look very different.
Well, no, it doesn't look that different.
Well,
I think what happened is
closer together.
well, I think what happened is that after one iteration, it's already there. Right? This does not show the starting point, it just shows the first iteration.
Oh.
So it just means it converges very quickly. But I think you can see that this ellipse is the same as the fixed point ellipse here.
Mm-hmm.
It's really the same. There's no difference. All right. All right, all right, so you talked about the bouncing around. Now, actually, we can, if you look at your sheet, we can make a very small modification and do this. Oh, all right, so the thing was that the other thing that you actually have here is for question 6, what you solved for were the fixed points depending on C. So so if you start at C, then the fixed point is given by that equation in 7, 1/2 plus or minus square root of 1/4 minus C. Okay. Now we also talked about how some fixed points are stable and some are not stable. A fixed point that's stable means that if you're close to the fixed point, every time you do the function again, you'll get closer and closer. Just like we saw here. We saw these fixed points were stable because you keep iterating, you're getting closer and closer to those points. Those are all stable fixed points. So the question is, which C's give you stable fixed points? And we solved that. We solved that. For it to be a stable fixed point, you need to have the absolute value of Z is less than 1/2. So we solved that inequality, and that's our region in space. And the boundary of that region is where the value is equal to 1/2. So if we plot that region, then we'll find all the points, all the C values that have stable fixed points. So when we did plot that region, and it's up here, you get exactly this shape. So the meaning of this shape is all points inside this shape have stable fixed points. They don't all go to the same point, they don't even go to the same region, but they all go somewhere and stay there. This, for you people in numerical analysis, this is actually very similar to Newton's method that we've been talking about. Newton's method, you start somewhere and you keep iterating the function, and you end up somewhere. That's a stable fixed point. Now, if you have a function with many roots, sorry, I said, if you have a function with many roots, you may have many stable fixed points, right? So you don't have to. It's not everywhere has the same stable fixed point, but if you got a stable fixed point, you keep going again and again, and you'll get in there, right? So any point with a stable fixed point is in the Mandelbrot set because it won't go out to infinity. That's the whole thing. Mandelbrot set is all the points that don't go out to infinity. All right? So the question is, these are the only points with stable fixed points. What about all those other black areas in the Mandelbrot set? What's going on with those? So that was the question. Okay. So remember, in the Mandelbrot set, there is this circle. And we'll do it here. There is this circle that's labeled 2 here. So the question is, these points do not have stable fixed points. So what are they doing? They're not going out to infinity. If I plot the points, they're not going out to infinity. Where are they going? What are they doing? Yeah, so that was the thing. So we can actually just make a very minor change to this code. Very, very minor change. Instead of this circle, where are we? Is it this one? It is this one. All right. Now, this is a circle with radius 0.05 with center at 0. Now, I want a circle with center at -1. Finished.
Okay, that's where that -1 came
Yes.
from. Okay.
Right. All right. So let's see what's happening now. And all right, now, so there you have it. You have two things like this. Now, this is a very small circle. That's why it looks like this. And this scale, and the reason why these are actually probably very close to circles, the reason why they look like that is look at this scale here. This is -1, and this is 0. This here is 0.04 and -0.04. So this vertical scale is very squished down, and this is a very long distance. But these points, if you look here, whoops, where'd the other circle go? Well, look at the scale here. This is just near -1.
Mm-hmm.
This circle here is the circle on the left. Look at the x scale. It's the same circle. So all the even ones are on this circle. And look at the odd ones look the same, but it's near 0. So all the odd ones are near 0. So it's bouncing back and forth between two things. So it's a non-stable fixed point. It's a point, what you call point of period 2. Right, period just means how long it takes to get back. All right, so the question is, are there points with other periods? And so let's go. And things get a little bit weirder when you make this circle bigger. This is nice. It's kind of interesting to see what happens when you make this circle bigger. This was radius 0.5, right? So let's.
I think it was 0.25.
Yeah, that was 0.25. But let's just work our way up and see what happens. Let's try 0.15 and see what this looks like. See if that's interesting. Whoops. Sorry, I pushed the wrong thing. Here we are. Is this the right one? Oh, no, this is not the right one. All right, let's try again. Let's see what it does. All right, so it's still kind of circular. So they're still kind of circular. Let's see if we can. But I think when you get close to 0.25, well, let's go up to 0.25 and see what it does. So it's kind of getting fireworks, sort of. Look at this. This is really a jumble over here. You get something. This is looking pretty regular, but here you've got something kind of strange going on. In fact, this is the beginnings of what is called mathematical chaos. So there is a mathematical notion of chaos. All right, so let's go to the reference here, and I guess I'll just type it in because I don't have it here. It was this was the reference that you have in your document. It's math.bu.edu, DYSYS, FRACGEOM, FRACGEOM.html. And here's the fractal geometry of the Mandelbrot set. So if you know anything about fractals, fractal is something that kind of is similar as you get smaller and smaller. You just keep zooming in and it looks the same. All right. So so there were some here. So I said that we look at pages 1 through 4. If we look at these, I'll open these in new tabs so we can look at them one by one. The first one just basically talks about what you're doing. Now, one thing that was interesting here that I didn't mention in the original definition of Mandelbrot set is, in the original definition of Mandelbrot set, I started with C. And then we started with f of C, f of f of C, f of f of C. But actually you can start with 0. Because if you start with 0, then the first one goes to C. So really you can think of every sequence starting with 0. And I think all this other stuff, it's just kind of a nice review to see how it works out. Okay, and here he's talking about, this is what's called an orbit, and he's saying what's happening when this bounces around. All right, so let's go to the next one, and here's where he mentions chaotic behavior. So if we look at this one, I don't know if it's going to come up or not. Looks like it's not. My computer's not having a good day. Not having a good day. All right, so anyway, let's go on to number 2. So you know all about Mandelbrot set, and we've talked about this, and you know that the colors, all of these color areas are not in the Mandelbrot set, and the more red it is, the faster it goes away. All right, so let's go to periods of the bulb. So this is where we talk about the periods. Okay, so here he talks about decorations. These are the little things hanging off the main bulb. And then if you zoom in, you see these things. And what he says, and I don't know how to prove it, is that this decoration has ornament here that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, I don't know. So that means that the points in here are period 12. If I plotted one point here, and I plotted several iterations, we'd see it moving around in a pattern that repeats itself every 12 times. Right? So, and he says there's a pattern in these bulbs. So my question in the paper was, find one with period 3. Okay, so do you see the period 3 over here? You see the bulb with period 3. Mm-hmm. All right. So we kind of know where to look. It's this here. All right. So so the question was, let's see. Yeah, it says locate. Okay. So. Yeah, it says locate a bulb of period 3. So this is the top of the second page. So there's my bulb of period 3 right there. So locate 3 points inside the bulb and make 4 plots. So how am I going? Where is this? What do you think the coordinates of this bulb are? Well, all right, they give you one. Okay, good. That's all right. That's even better.
Right at the top.
Yeah. Okay, there's one at period 3. So minus 0.12 plus 0.75i. Okay. So let's give it a shot. All right. So in fact, you could possibly kind of eyeball it cardio. So let's give it a shot. So what I want to do is start. So what it says is, I want, instead of 3 plots, I want 4 plots. Okay. I want to do all of the iterations, and then I want to do 0, 3, 6, 9, etc. And I want to do 1, 4, what's 4 plus 3? 7, etc. And then 2, 5, 8, and so on. I'm going to make 3 separate plots. All right. So let's go here and see if we can modify this. It's really quite similar to what we've already done. So let's go here and we'll copy this code. This one here, this beautiful code here. And copy is escape.